Hey folks, in this video we're going to look at the answers to the problems from Group Project 1. First problem requires that we draw Lewis structures, determine formal charges, and geometries of the corresponding structures. So we'll start with the carbonate ion. So, of course, the first thing we'll draw Lewis structures, we have to count up the total number of valence electrons. And so without going to the periodic table, I'm going to rely on you doing this just to ensure that you know how to do it. Carbon has 4 electrons. Each of the oxygens has 6 electrons. And then, of course, we've got an extra 2 electrons because it has a -2 charge. So we have a total of 24 electrons. All right, so we'll go about the normal way of doing this. And again, without going into specifics, since you've done this before, we can start by drawing the single bonds to the oxygens. Let's take care of the oxygens and draw the non-bonding electrons to satisfy the octet rule for all the oxygens. And we can do that. But at this point, what we're going to note is that while the octet rule is satisfied for each of the oxygens, it's not satisfied for the carbon. The carbon only has 6 electrons around it. So we have this situation where we have not satisfied the octet rule for every atom in the species, and we've run out of electrons. So when that happens, what we need to do is we need to actually create multiple bonds. So we're going to do that by eliminating some non-bonding electrons on one of the oxygens and drawing a double bond in for that situation. And we can see that will now work. We now have satisfied the octet rule for all the atoms in the ion. And we've used all of the electrons, all of our valence electrons for the beast. And so we're good. Now, one thing to note here, however, is that when we have a situation where we have multiple bonds, and we only have a multiple bond in one situation, there is no reason why we couldn't have drawn it for the other atoms. And so we can draw these structures for all of the others and simply switch the positions of the multiple bonds. So as you can see from these, that we now have a total of 3 structures. The only difference between the 3 structures is placement of the double bond. And of course what this means is we have these resonance structures now that show that each of these bonds is equivalent. Of course, the reality is that in nature, the real molecule is a weighted average of all of the resonance structures. So in that particular case, that means each of the bonds is equivalent when we do the weighted average. And sometimes you might see it drawn like this to indicate that we've got this weighted average where these electrons are delocalized over the entire molecule. All these bonds are equivalent. They all have the same bond length. So that is the point of having resonance structures. It shows in nature that what the real molecule is going to behave as, it's going to act as a weighted average of all of these. So this is the structure. Now, when we look at any one of these, of course, we know that we've got 3 groups of electrons, and that means that when we've got 3 groups of electrons around our central carbon, we've got a trigonal planar structure with roughly 120-degree bond angle. All right. Now, what about formal charges? In the case of formal charges, we need to discern the formal charge on each of the atoms in the molecule. I'll just do one of them here. And the way we do formal charges is we're going to take the number of valence electrons for each atom, subtract from that the number of non-bonding electrons, called as NBE, and subtract from that the number of bonds. All right, so if we look at the carbon here, so in the case of the carbon, the formal charge is going to be, we've got 4 valence electrons, It's got no non-bonding electrons. It's got 4 bonds, so its formal charge is going to be 0. All right. For the oxygen, which has a double bond, we've got 6 valence electrons for oxygen. The oxygen with the double bond has 4 non-bonding electrons and has 2 bonds, so its formal charge is 0. And then for the remaining oxygens, which with the single bond, at least in the individual resonance structure, we've got a situation where we got 6 minus 6 minus 1, so each of those is -1. So we're going to just simply write this in with a little number associated with each one. So the formal charges for each of these is indicated with that number. That's how we'd indicate it. Now again, remember that the total of the formal charges, if I add up all the formal charges, it should be equal to the charge of the species, and indeed it does. The total is equal to 0 on carbon plus 0 on the double bonded carbons plus -1 plus -1, and that's a total number -2. So that does satisfy that requirement for the carbonate. So we've got 3 resonance structures, and you should draw all 3 in this case. All right, so let's move on to IF3. We'll do the same thing here when we do IF3. We're going to have for the iodine, it's in column 7. The fluorine's in column 7. All of these beasts have 7 valence electrons. So the total number of electrons is equal to 28. 4 times 7. All right. And again, let's just go ahead and start by drawing it. When we have 28 electrons, we can distribute those electrons to satisfy the octet rule for each of the fluorines. When we do that, at this point, after having drawn it, what we have is a total of 24 electrons, right? 8 electrons around each of the fluorines. And we've got 4 electrons remaining. So we're going to put that on the iodine here. So we got 2 non-bonding pairs. Now notice, of course, the iodine has now 10 electrons around it. It does not satisfy the octet rule. That's okay, because when we get to the heavier atoms and we have empty d orbitals available in the valence shell, then we can exceed the octet rule in these circumstances. So we've got 5 groups of electrons around the central atom. This is trigonal bipyramidal structure with 5 groups. Noting that the non-bonding electrons are going to be on the equatorial plane in this case, and so we're going to end up with a T-shaped structure in this circumstance, and that angles are going to be 90 degrees here for that. Okay, so that's going to be the case for the T-shaped structure, which is based on the trigonal bipyramid, not trigonal pyramid, the trigonal bipyramid structure. Now, in terms of formal charges here, it looks like I missed 2 electrons there on that fluorine. In terms of the formal charges here, we use the same rules, and for the fluorine, 7 valence electrons minus 6 non-bonding minus 1 bond is going to give a formal charge of 0. And for the iodine, we've got 7 valence electrons. We've got 4 non-bonding electrons and 3 bonds, and so that's also 0. So all of the atoms in this species have a formal charge of 0. We have no multiple bonds here, so we have no resonance structures for this particular beast. All right, moving on to sulfur tetrafluoride. All right, so how many electrons do we have? In this particular case, sulfur has 6. Each of the fluorines has 7. as we've noted earlier. So we've got a total of 34 electrons in this situation. And with 34 electrons, we're going to draw it. I'm drawing a dashed wedge structure, and I'll explain that in a couple of seconds if you haven't been exposed to this before. We're going to have the situation where satisfying the octet rule for each of the fluorines, we're going to find that we have 2 electrons remaining that are going to go on the sulfur as a non-bonding pair of electrons. Again, we've got 5 groups of electrons around the sulfur, and that means we've got a trigonal bipyramid basis. And that means, and in this case, the seesaw, that's going to correspond to a seesaw structure. And the bond angles are going to be between the axial fluorines and the equatorial fluorines. It's going to be 90 degrees, actually a little bit less than 90 degrees. And that's important to note. Of course, the non-bonding pair of electrons tends to squeeze those things together. That's also going to be the case for the T-shape, that these angles are going to be less than 90 degrees because of the presence of the non-bonding electrons on the iodine. So it's going to be less than 90 degrees. And then between the fluorines and the equatorial plane, it's going to be less than 120 degrees in that situation. Okay, what about formal charges? The fluorines here, you'll note, really have the same number of electrons and same bonds as they did in the iodine trifluoride. And so we're going to go ahead and note that all the fluorines, without recalculating, are going to be 0 formal charges. What about the sulfur? Well, one should hope at this point, because this is a neutral molecule, since all the fluorines are 0, the sulfur should be 0 as well, but let's just check that for the sulfur. Sulfur is in the same group as oxygen. It's got 6 valence electrons, all right? It's got 2 non-bonding electrons, and it's got 4 bonds, so it's got a formal charge of 0. So all of the atoms in this molecule also have formal charges 0. Again, no multiple bonds here, no resonance structures in this particular circumstance. Okay, what about ozone? All right, ozone, O3, 3 oxygens. We have 18 electrons because each oxygen has 6, all right? And we're going to distribute those oxygen electrons. Again, we can start like we did before by trying to satisfy the octet rule for every one, but the best we can do with 18 electrons without multiple bonds is going to see that we're not going to be able to satisfy the octet rule for every atom. And again, remember, when we have a situation like that, what we need to do is include multiple bonds. So what we're going to do is take one of the non-bonding pairs and draw a double bond there, and now we can see that we've satisfied the octet rule for every oxygen in this case. But again, here's a situation where we have a double bond and a single bond, and there's no reason that we should pick out a particular bond as being a double bond. We've got a resonance structure here where we can draw the double bond on the other side. And again, what that means is that in nature, the actual molecule is an average of these, and that means that these bonds are going to be the same. All right, so this is based on, we've got 3 groups of electrons around our central atom. All right, remembering, of course, the double bonds just count as one group of electrons. So 3 groups of electrons means that we've got a trigonal planar structure. All right, with bond angles of 120 degrees. Of course, we're going to call this bent. All right, and the bond angle is going to be somewhat less than 120 degrees again, because the lone pair of electrons will squeeze. The repulsion kind of squeezes them together, so it is less than 120 degrees in that situation. What about formal charges? If we look at this oxygen here, the formal charge is 6 minus 6 minus 1, so that's negative 1. For this oxygen here, it is 6 minus 2 non-binding electrons, minus 3, so that's a plus 1, okay? And this oxygen here is going to have, I'm not going to go through it, it's going to have a formal charge of 0. You should make sure that you understand that. So we've got negative 1, plus 1, and 0 as our formal charges for that, for ozone. Okay. All right, so that finishes our discussion for problem 1, where we're drawing Lewis structures, determining geometries, and formal charges. If you have any questions, make sure you ask.